Hi, and welcome to another R Labs tutorial. In the previous tutorial, we learned how to represent population dynamics such as exponential growth and logistic growth with difference equations. Now, up to this point, the logistic growth dynamics that we examined have been quite simple and predictable, like this. We get a steady rise to equilibrium, after which point the population size remains quite constant. But the dynamical properties of the discrete time logistic depend on R. And when R is high, the dynamics of populations begin to look quite messy or unpredictable. For example, these data on a laboratory population of blowflies do not seem to reveal any real pattern. The population does not appear to remain constant in later generations. Now, it is certainly possible that this messiness is extrinsic, driven by some outside factor, but it is also possible that the messiness is a pure intrinsic signal of the population. Let's take a closer look at this discrete time logistic equation and how chaos might arise. So recall the difference equation that we looked at previously, where nt plus 1 is the new population size, nt is the old population size, r is the per capita birth rate minus the per capita death rate, and k is the carrying capacity. Now, if you do a little bit of mathematical magic, you can derive a simplified canonical form of this discrete time logistic. So in this canonical form, we now have xt plus 1, which is the new ratio of the existing population to the maximum possible population. We have r again, which is still the per capita birth rate minus the per capita death rate. And then we have xt, which is the old ratio of existing population to maximum population. So in effect, the x terms here incorporate both k, the carrying capacity, and the respective n terms from the initial equation. Now, as I mentioned before, the dynamics yielded by this relationship here depend on the value of r. So in early generations, we might see this typical steady rise in a population size. But we're actually going to look today at what happens in later generations. Well, with low values of r, the population size can reach an equilibrium after a steady rise and then stay at approximately the same size. This is called a one-point cycle because one point is repeated over and over. But as r increases, we start to see oscillations. First, we might see two-point cycles, whereby the same population size is repeated every 2 generations. So there are 2 population sizes that are repeated over and over. As r increases even more, we might see 4-point cycles, where the population size repeats itself every 4th generation. So 4 different population sizes are repeated over and over. And as r continues to increase, the dynamics oscillate more and more until eventually there is no distinguishable pattern of oscillations. We call this chaos. Now I'll show you some similar plots in R just to demonstrate that this can in fact be represented in R. So you have seen code very similar to this in the accompanying video. Here we have the function containing the difference equation. And then here, I am generating 3 different vectors of population sizes using the above function, and I have used 3 different r values, r equals 2, r equals 3.5, and r equals 3.9. And now I'm just plotting out the generations versus the population size for each of the 3 cases, and I've specified that I want the 3 plots to be generated side by side for comparison. As you can see for this low value of r equals 2, we have a 1-point cycle. Then at higher values of 3.5, we see a 2-point cycle, and at an even higher value of 3.9, it looks quite chaotic. This change in dynamics with different values of r can be visualized well with a bifurcation diagram, such as the one shown here. Essentially, this diagram shows the different population sizes in later generations for different values of r. So you can see that for small values of r, there is only one population size that appears in the last 9,000 generations in this case. So this range of r values produces 1-point cycles. Then as r increases, we eventually see that 2 different population sizes arise in the last 9,000 generations. So this range of r values generates 2-point cycles. Then we get 4 population sizes that arise, so here are the 4-point cycles, and so on and so forth. And as you can see, the period of cycle doubling occurs over an increasingly smaller range as R increases until we reach the chaotic regime, where innumerable population sizes arise in the last 9,000 generations. Now, interestingly, we see a period of predictability amongst the chaos here at high R values. This is called period 3. So now I'm going to show you how to generate one of these bifurcation diagrams in R. So if you recall from our example of a bifurcation diagram, we want to be plotting out multiple R values against the population size or sizes associated with each of the R values. So the first thing we have to do is determine the R values that we want to use. We'll have a minimum R value called min R, and I've set that equal to 2.5. Then we'll have a maximum R value, max R, which I will set to equal 4.0. And let's say that we want our R value to increase from 2.5 to 4.0 in increments of 0.01. So here I've set an inc variable equal to 0.01. So now we can go ahead and make a vector called RD containing these R values. So we'll create a sequence from the min R to the max R in increments specified by the inc variable. Good. So now we have the R values covered, and we can move on to the time component. With bifurcation diagrams, we know that we want to examine the later generations. So in this example, let's say that we only want to start collecting data for the plot after 100 generations. So we will say T transients gets 100. This represents the period that we will ignore due to transients. And just as a side note, the term transients refers to the route to the attractor, the route to the equilibrium. So essentially the transients are the outputs in early generations before reaching an equilibrium or attractor. Now we also have to decide over how many additional generations to collect data on the population sizes that arise. In this case, let's collect data over 400 generations. So we'll say T range gets 400. Now we're going to generate an empty plot and then fill it later. And finally, all we have to do is use a nested for loop to generate our data. So the first for loop cycles through all of the values of R, meaning that everything within this first loop happens to each R value in turn. For each value of R, the initial population size, x in this case, is 0.1. We know that the population changes with each generation, so this second for loop loops through 100 generations, i.e. the generations from which we don't want data, in order to continuously calculate the new population density values. Finally, the third for loop loops through 400 additional generations to continue to calculate the new population density values that we do want to plot out. So in addition to simply calculating the values, this for loop plots out all of the points on the empty plot as well. Now, continuously plotting points like this can take R a little bit of time. So an alternative route would be to store the data in a matrix and then plot them out all at once. This alternative code is included in the accompanying R code document in case you're interested. Thanks for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.